Hi everyone, we are Team SUDOS, the Smart Urban Delivery Optimization System. Our project applies DAA paradigms, Greedy, Dijkstra, Floyd Washer, DPTSP, and MaxFlow to solve real-world urban delivery routing. Think about platforms like Amazon, Swiggy, or Blinkit. Every day they handle thousands of deliveries across a city. The core challenge assigns agents efficiently and compute the shortest, cheapest routes. We model the city as a weighted graph, locations as nodes, roads as edges, and our five objectives are model the graph, assign requests optimally, compute routes, compare algorithms, and analyze the trade offs between speed and optimality. Our first algorithm is the greedy nearest neighbor heuristic. Starting from the depot, it always picks the closest unvisited delivery point. Next, simple and fast at time complexity O of n square. It works great for large graphs where you need a quick answer. The trade-off, it's not globally optimal and can get stuck in local choices, but it's excellent baseline.
Next is Dijkstra's algorithm. We use it to pre-compute shortest paths from any source across the city graph. It uses a min heap and runs at O of v plus e log v time complexity, guaranteeing the shortest path for non-negative weights, exactly like GPS systems do. The limitation is it only handles a single source and it doesn't directly solve full delivery problem. For exact optimal routing on small delivery zones, we use the held carp algorithm. It uses bitmaps DP where each state tracks which cities have been visited. Its O of 2 power n square is 100% optimal but only feasible for up to 20 nodes. Think of it as gold standard for high precision deliveries like medical logistics.
For larger zones, we use nearest insertion, an approximation algorithm that's proven to give routes within 2x the optimal. It runs at O(n) square and scales to thousands of nodes, making it practical for real-time delivery scheduling, where a near optimal answer is perfectly acceptable. We are talking about the heuristic TSP, how it works. We have to start with a partial 2, find and then find unvisited city nearest to any city in the 2, then insert it in the tour position with minimum cost increase and repeat until all cities are inserted. The advantages for this are bounded approximation ratio, practical for real delivery, much faster than exact TSP, scales to city level routing, easy to implement variants. Disadvantages are not globally optimal, quality depends on heuristic, may still be slow for huge, and approximation ratio varies. It's hard to quantify exact gap. Next, finally, MaxFlow handles the agent assignment problem. We build a network, source to agents, agent to orders, orders to sync, and run min cost MaxFlow to optimally assign each delivery to the most efficient agent. It's ideal for multi-agent dispatch with fleet capacity constraints. Its advantages are optimal agent assignment. It handles capacity constraints, multi-agent aware, flexible cost modeling, and scalable to fleet routing. Here's a side-by-side comparison. Greedy is the fastest and most scalable. Dijkstra handles single source shortest paths optimally. DPTSP is perfect but limited to small inputs. Approximation TSP balances scale and quality. MaxFlow is the right tool for agent dispatch. The key insight, no single algorithm wins everything. Pseudos use them together. SUDOS maps directly onto real platforms. Blinkit uses Greedy plus Dijkstra plus Maxflow. Amazon uses Floyd Warshall plus Approx TSP. Swiggy uses Greedy for rider assignment, medical logistics demands, exact TP-TSP. Even Uber and Ola use the patterns for ETA and surge balancing. Essentially, SUDOS is the algorithm layer behind every delivery you track on the phone. To summarize, greedy for speed, Dijkstra for the shortest path, DPTSP for exact small routes, approximation TSP for scalable delivery, and MaxFlow for optimal agent assignment. Together, they form pseudos. Thank you. We are happy to take any questions.
So, hello everyone. This is our project SUDOS, Smart Urban Delivery Optimization System. Three of my friends have already presented the PPT on the various shortest path algorithms, their advantages, disadvantages, their working, and in which situation which algorithm is better. Now I, Nihar Reddy, I'm going to give you the demo of our project, SUDOS. So this is the core interface, and we simulate a city. Basically, this is the whole city, and we are taking nodes and routes. So nodes is like a location of different places in the city, and routes are like roads basically through a city. So in this virtual city, you can add location. For example, I can show you this. For example, you can add a node which says 10. This is the added location, and you can also add routes. For example, from 8 to 10, we can enter the travel distance. For example, 7 to this specific one, and this creates a route. So now the next step is we can set a warehouse that let's set as the node 0, this particular node, and we can also set customer, like where it has to actually go. We can select multiple customers also, because you're using different agents to go different locations. So let's also give 4, and let's also give 3 as the 3 customers which are gonna go. And let's also we can also simulate multiple delivery agents working simultaneously. So let's go for 3 agents in this one. There's also a option to clear city map, which basically erases everything and you can start afresh. Now the main part comes, in which you're selecting the routing algorithm. There are different algorithms which my friends actually explained earlier. There is Floyd-Warshall, there is Dijkstra, there is nearest neighbor. Let's take an example of Dijkstra. For example, if it's Dijkstra, for this specific graph, we have set the warehouse, the customer, and now we can click on Run Delivery Auto, and it's gonna show you the different stages, and it's gonna give you the conclusion. So what it's giving is the dispatch is complete and the total fleet distance and the highlighted paths of all the 3. For this is the blue path, this is the orange path, and this is the green path. It also gives us the time, cost, and complexity. So this is for one of the thing. Let's take for Floyd-Warshall. We'll keep the same number of agents is equal to 3, and we'll run delivery, and it also gives us the same result with total 48 and similar things. We can also go for heuristic TSP. So it's building, and these are the steps. It shows the intermediate steps. If you want, you can pause the project and move to each step to check each step. So yeah, through this we got a different one. So we got the approx fleet distance, we got the time, cost, and complexity. So this is the basic idea of a project. We are basically displaying a city, and using this project through different algorithms, we can check like to what are the paths that the agents are going, that the agents are taking, and in how much time, in how much cost, and in how much complexity they're actually reaching those destinations. So this is the whole idea. Thank you for watching this video, and